If the function f of x is positive, continuous, and decreasing for x greater than or equal to 1, and a sub n is equal to f of n, then the sum of a sub n from 1 to infinity and the integral of f of x from 1 to infinity either both converge or both diverge. You may have a series represented with summation and the a sub n term. If you integrate the a sub n term as if it were a function, an improper integral, then the behavior of that improper integral is the same as the behavior of this series. Note that the actual sum, the actual value of the series, is not equal to the actual value of the improper integral. So even though these are not equal, the behaviors are the same. A sub n as a function would be 1 over n squared plus 1. This associated function is positive. It has a horizontal asymptote at y equals 0. It is decreasing. Each term is getting smaller than the term before. And it is a continuous function. Notice how there are no asymptotes or holes. Now we can write it as an improper integral. We start at 1 and go to infinity. This is an improper integral that we need to write as a limit. If you recall, the integral of 1 over n squared plus 1, the integral of 1 over n squared plus 1 is arctan of n. I can separate the limit. And arctan of 1 is the angle for which tangent of that angle is 1. That would be pi fourth. Recall that the graph of arctan has a horizontal asymptote. So as t approaches infinity, arctan of t actually does approach a value. That horizontal asymptote used to be the vertical asymptote for tangent, and that would be at pi halves. Pi fourths, we have a value. That means this integral converges. And if the integral converges, then the associated sum will also converge. That is known as the integral test. The function 1 over n ln n is positive for all values greater than 1, and see we're starting at 2. It is a decreasing function. Each term is going to be less than the term before it, and there's no way for us to get a negative value, so it is positive. This graph does have a vertical asymptote at n equals 1, but again, that's not within our limits of integration, so the corresponding function is positive, decreasing, and continuous, so we can use the integral test. I rewrote the integrand because I think it's a little easier to see that we have u prime over u, which gives us ln absolute value u. And here we have a divergent integral, which means our associated series will also diverge. And instead of writing integral test, we can put IT. Let's try number 3. In fact, not only does the series diverge by the integral test, this series appears so frequently that it has a special name all in and of itself. This is called the harmonic series. It is known that the harmonic series diverges. If you ever had to compare or use this series, all you would have to say is harmonic, so it diverges. Let's try the integral test for number 4. This is a divergent integral, which means the corresponding series will also diverge. Do you have a prediction for number 5? The associated function would be 1 over n squared, so our improper integral would be 1 to infinity of 1 over n squared. And let's evaluate it. This integral is convergent. And if the integral converges, then the corresponding series will also converge. You may have noticed a pattern with our previous 3. All of those series are considered p-series. If p is a positive constant, then this is called a p-series. If p is greater than 1, then the p-series converges. If p is greater than 0 and less than or equal to 1, then the p-series diverges. For the geometric series to converge, r must be less than 1. For the p-series to converge, p must be greater than 1. Here's the harmonic series in which p equals 1. That is known as a divergent series. Use the p-series test to determine the convergence or divergence of these series in examples 5 and 6. First, I want to be able to see what p is. I could rewrite this as over 1 root 1 to make it look like the rest of them, and then I think I could build an nth term from that. That would be 1 over n root n, obviously starting with 1. Now n root n can be combined. That would be n to the 3 halves. This is a p-series. P is equal to 3 halves, which is greater than 1. Therefore, this series converges by the p-series test. I'll rearrange what's inside of our sum to figure out what p is. In this case, p is 2/3, which is not greater than 1. Therefore, this p-series diverges. And we could put PST instead of p-series test.